This week we're looking at 6.2, which is exponential functions. So we're going to start just by looking at the graph in a table of f of x equals 2 to the x. So that x is in the exponent right here. So any value that we plug in is going to be a power. So looking at the table, let's look at the graph first actually. So in this graph I marked off some points. Basically, as we plug in these values, though, it's going to create this curve which has a slow increase, and then it starts to get really, really steep. And the greater the x value that we plug in, the steeper it'll get. So at some point, it'll look practically vertical, although it's not exactly vertical. So that is the graph of 2 to the x. So the values on this, let's look at these here. We plug in a -2, we get a 1/4. And the reason for that, there's a property that we need here. So 2 to a negative number, or anything to a negative number, is the same thing as 1/2 to the positive of that number. So this would just be 1/4. So that's going to be how that is for all of these. So if we plug in a -1, this would be 1/2 to the 1, or 1/2. So negative exponents are just fractions. They're just rewritten. So as we look at the values as we go down, it goes from 1/4 to 1/2 to 1 to 2 to 4 to 8. So you can probably see a doubling pattern. So right here, 1 times 2 is 2. 2 times 2 is 4, and 4 times 2 is 8. Now, if we look at this from the top, you can see that if you have 2/4, that's the same as 1/2. So that's still times 2. 1/2 times 2 is 1. So for all of these, it's a doubling that's happening as the y values get larger. So that's what's going to happen for all of these exponential functions. They're going to have some ratio that is consistent as each x value increases by 1. Okay, another thing I'd like to look at on this graph, you can see the red line gets really, really close to the axis here, or the black line. And although it looks like it would touch, this will never actually touch the axis. So this is always going to be something above 0. So this is called an asymptote. So this line will never be crossed. So we would say in this that y equals 0 is an asymptote. Okay. And that's because any fraction or any number that we plug in, it'll just create a really small fraction, but it'll never be negative. So let's go to an example using application. So in this one, it says a network administrator uses the function f of x equals 5 to the x to model the number of computers a virus spreads to after x hours. If there are 1,000 computers on the network, how many hours will it take for the virus to spread to the entire network? So it's giving you the function 5 to the x. And so what we're going to do is plug in positive numbers and see what the y values are, see what happens. So let's plug in a 0. So since x is representing hours, it's time, so we're not going to use negative numbers at all. So if I have a 0, so I go 5 to the 0, anything raised to the 0, doesn't matter if it's 1,000, 10,000, a million, negative 1 raised to the 0, it's always going to be equal to 1. So anything raised to the 0 power is 1. So this value is 1. If we plug in a 1, we have 5 to the first, which is 5. If we plug in a 2, we have 5 squared, which is 25. Plug in a 3. 5 to the third is going to be 25 times 5. So you'll have 125. 5 to the fourth. It's going to be 125 times 5, so that would be 625. And then once we get beyond that, the numbers start increasing very quickly. So the next number would be 3,125. And I'm going to stop there because I actually went over 1,000. So I'm going to plug in my numbers here. So I have 125. At 4, I had 625. And at 5, I had 3,125. So it says about how many hours will it take for the virus to spread to the entire network? Well, this is a huge range of hours here. So it's definitely between 625 and 3,125. So for this one, we're going to go to a graph and just take the value from the graph because that's the easiest way to do that for now. So I will pull up a graph. So I'm using Desmos, which you should use too. Just an online calculator, but it's one of the best ones. I'm going to plug in 5 to the x. Okay. So it gives me an exponential function, which is good. It's this blue line. And if I, point at that, so I'm using a stylus right now, but I can actually see where it hits 1,000. So I'm going to move this graph down. Doesn't quite do it there. And I'm just going to see where it gets to 1,000. So here's 1,000. If I go up right there, it tells me that it is at about 4.29. Let's actually go up a little further. There it is. It goes over 1,000. So 4.293. So let's go back. So it's after about 4.293 hours that the virus infects 1,000 computers. Okay, so sometimes you're going to have to use a calculator to pull up those values, and I encourage you to use Desmos. It's free, it's online, and it works really well. So that would be the solution to that. So we made a table. I found about where it would happen. It would happen between x equals 4 and 5 because my y values were 625 and 3,125. Then I went to the graph and just took the value from the graph. Okay, so for this one, we have a table and it's asking us to find the function. So exponential functions come in the form of f of x equals a times b to the x. The b represents the factor by which it's decreasing or increasing. So b is going to be by factors. So what I'm going to do first is start out figuring out what that factor is. So at x equals 0, we have the value 4. And then we have that it goes to 12. So the easiest question to ask when you do this is 4 times what number is 12? And 4 times 3 is 12. So if this is a consistent value all the way down, then it will be b. So as 12 goes to 36, what do you multiply 12 by to get 36? 3. 36 times 3 is 108. And 108 times 324, or 108 times 3 is 324. Don't need that last one. Okay, so I know that my b value is 3. So this is definitely 3. Okay, the next place that I look on the table is when x is 0. Because what this is going to tell me is my starting value. So this tells me what a is. So if I plug in a 0, I get 4. So that means that a is 4. And this is just raised to the x. And so the function f of x equals 4 times 3 to the x is what is represented by this table. So you're looking for two things. You're looking for your starting value, so when x is 0, what is f of x? And you're looking for the number that is multiplied to get the resulting y values. Okay, so this is another one where it's a find the function. So the easiest way to do this, it gives me all these values. The only difference here is that it's not on a table. So let's just make a table. And then it would be exactly like the last problem. Okay, so if I just take these values from here, 0 and 128, 1 and 64, 2 and 32, 4 and 8, and then 5. I'm going to add one more to this graph, so I'm going to actually move this down. Let's look at 3 here. So at 3, looks like it's about there. That's at 16. And then at 4 we have 8, and then 5 we have 4. So now we have the table, so this is exactly like the last one where we're going to use that the table to create the function rather than the graph because it's easier to look at the data. So f of x equals a times b to the x, so we just need to find a and b. So as I go down from 128 to 64, what number would I multiply 128 by to get 64? It's half of 128, so I'd multiply by 1/2. 64 times 1/2 is 32. 32 times 1/2 is 16. 16 times 1/2 is 8. And 8 times 1/2 is 4. So since I have a consistent ratio as I go down here, that would mean that my b value is 1/2. So I'm going to put this in parentheses and then put the x outside. Now I go to the table and look at my 0 coordinates, so that's 128, so this is 128 out here. And there it is. So f of x is 128 times 1/2 raised to the x. So let's look at this graph. We can look at that one, and it is decreasing. So the other functions, if we looked at those, let's go to the other picture here. That graph was increasing, and its ratio was 2. So b is 2 in that case, and in the problem that we just did, or currently doing, it's 1/2. So if you have a decreasing function, the b value will be a fraction between 0 and 1. And if you have an increasing function, b will be a whole number, or a number over 1. Okay, so for this one, we're going to just compare these two things. So let's look at, we're going to compare the faster way to get money, or how money would be, which function grows faster. So in this first example, it says you're given $100 to start, and then you'll save $25 each week. So I'm going to fill out this. So if 100 is my starting point, that means x equals 0. I would have 100. And then on week 1, it says it's going to add 25 each week, so I'd have 125, 150, 175, 200, and 225. Do one more here, 250. So this is, let's talk about this. This is when we're adding 25. So this is not exponential growth. This would just be linear growth because we're adding the same amount each time. So you're just adding 25 each time in that one. So let's say you were given $1 to start, and each week the value triples. Well, let's do that. So x and f of x on week, you're given $1 to start, so that's on week 0. You have $1, and each week the value triples. So after 1 week, you'd have 1 times 3. After 2 weeks, you'd have 3 times 3. After 3 weeks, you'd have 9 times 3. So just to clarify what's happening, we're multiplying by 3 each time. And there you go. After another week, this would multiply by 3, so you'd have 27 times 3, which is 81. Color change, if that's okay. 81 times 3 is 243. Then after that, it starts to get, increasingly large. 243 times 3 is 729. And you can see that it's going to continue to get really big after that. So 2187. So I'm sure most of you have heard things growing exponentially is a way to get, increase things faster. And that's because if you look at the two charts, even if you're given $100 to start and $25 each week, by the time you get to week 4, or week 5, I'm sorry, I'm going to circle those in that chart. So at week 5, if you have linear growth, even starting with $100 and getting $25 each week, you'll have $225. But if you look at week 5 from the exponential growth, we would have $243 on that week. So at week 5, that's when you would start to surpass the linear growth. And then after that, it goes crazy. By week 6, you have almost 3 times as much money with exponential growth. So if it were me and I were choosing a plan, this is the one I'd choose. And that's because exponential growth grows a lot faster than linear functions.